Good morning, welcome to lecture 18, which is titled The Fourier Operator, and you probably heard of the Fourier transform. Well, it's exactly the same. The Fourier transform is an operator, and in fact, for instance, you can calculate its spectrum. The word transform somehow hides that fact. We had this before with the BLT theorem, which will also play a role today. It's the theorem on density-defined bounded linear transformations, meaning bounded linear operators. So the Fourier operator will be today's topic. And in fact, this is not for its own sake, although you probably already met that in the experimental part of the lectures, right? You had Fourier transforms and momentum space and stuff like this. Did you meet that? Yes? No? You did not? Okay, even better. So there is a purpose to this, and the purpose is that with this lecture, we start a new part of the course. We start a systematic exploration of so-called Schrodinger operators. And these Schrodinger operators are operators of the following form. They're of interest as Hamiltonians of a system, but of course for the abstract theory it doesn't matter whether you call that then the Hamilton or the energy observable of the system. But the idea is that if you look at operators with a certain domain, it's always about operators on L2 or some subdomain or R to the D. A Schrodinger operator is an operator that acts on its domain like this, that the operator applied to a function psi yields the following function, minus h bar squared by 2m Laplace operator on psi at x plus v of x times psi of x, where this here, as I just said, is the Laplacian. This is d by, well, is d in the first direction squared plus d in the second direction squared plus d in the dth direction, the dth slot, I should say, squared. That's the Laplace operator. And this here is what one usually calls the potential. It's just a name. So that's a function from Rd into the real numbers. And the significance of these Schrodinger operators is that they define the right-hand side of the Schrodinger equation. Or if we express it in terms of our axioms, these are the operators that for particles that live on some Rd, so the typical case would be d equals 3, that particles that live on a three-dimensional real physical space, so that quantum mechanics looks at the square integrable functions on there, that the generator of the time translations, so the generator of the unitary time evolution, is of this form. And we saw something like this before, I think in one dimension. This is, of course, the momentum operator squared by 2m plus the potential. So this really looks like the classical Hamiltonian, but made into an operator. We talked about quantization and what it could mean and not mean. Well, it's, in a sense, it defines quantum mechanical problems in R3, on R3, that also where the particle in question feels this potential. Okay, so this is of very general interest, and textbooks, of course, discuss a whole number of situations where this v of x is given, and then you discuss that case in particular. We also did that. I took v of x to be m omega squared x squared. That was the harmonic oscillator. You can take this v of x, and you did this in the experimental part, I know. You took this to be a central potential given by something like minus some constant 1 over x1 squared plus x2 squared plus x3 squared square root. So 1 over r, if you wish. Okay, it's the central potential, a very particular central potential. It's the Coulomb potential or the Kepler potential, but you applied it in electrostatics, so it's the Coulomb potential. These are all special examples, and of course the solution of the harmonic oscillator, so for instance the eigenvectors, vary wildly if you change the potential. The eigenvectors of the harmonic oscillator are very different from the eigenvectors of, say, the hydrogen atom, and so on. Okay, so this is what this is, but the question is, can we study this in a more systematic manner, or do we really have to go example by example? Well, of course, physics often demands you not to consider the problem in its general position, as the mathematician says. That's the problem in general position. What can you say about this in general? Maybe making assumptions on the potential and so on. In physics, very often we consider a problem in special position. I'm interested in the hydrogen atom, and then I don't care about the general theory. But if we really claim to understand something about quantum mechanics, we need to study this in higher generality, in greater generality. And that's what we're trying to do in the next few lectures. And the Fourier operator is an indispensable tool in conducting that study. That's it. Okay, so the Fourier operator is an indispensable tool in conducting this study. And it's also very useful, sometimes maybe indispensable, in special problems. So this is not only a tool for this general theory. So let's start with the definition. So ultimately, we wish to define the Fourier operator on all of L2, but initially we cannot, and explicitly we cannot do it different than this. We look at the Fourier operator on Schwartz space. So you recall that we defined Schwartz space S of R for the real line, and we now extend the previous definition, which you now had sufficient opportunity to practice, extend the previous definition of Schwartz space on the real line to Schwartz space S on RD. This is as simple, it's precisely the same idea. A Schwartz function is a function that decays sufficiently rapidly if you go to infinity, and also has nice properties under differentiation. Precisely speaking, a function that is at least smooth. That's the set from which we pick Schwartz functions. And we impose 2 times a countable infinity of conditions. We impose that the supremum, if you look at any point x now on RD, we take the absolute value of an arbitrary power x alpha of x and an arbitrary derivative del beta acting on the function, evaluating at x, and we require this be less than infinity. So this looks exactly like what I wrote before, with the slight difference. I now say this must be true for all alpha and beta that come from n0 to the dth power. What is that supposed to mean? Well, and what is it supposed to mean? If x is in RD, what do I mean by the alpha power of an RD element, and the alpha itself is a d-tuple of non-negative integers? Well, very simply, this is just very convenient notation. What we mean by x to the alpha, again, x in RD, and alpha in n0 cross, so Cartesian product with n0 d times. What we mean by this, the x has components x1, x2, x3, up to xd, right? and we take the first component of x and raise it to the alpha first power, because the alpha is a d-tuple. And we take the second component of x and raise it to the alpha second power, times dot, 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 dot. We take the dth component and raise it to the alpha dth power. This is what you can do, and this is what this means. It's called the multi-index notation, but it's as simple. And the del beta is similarly defined. So on RD, you have partial derivatives with respect to the first slot, with respect to the second slot, and finally with respect to the dth slot. And you can take the first derivative beta 1 times, you can take the second derivative beta 2 times, dot, 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 and finally you take the dth derivative beta d times. That is what I mean by the symbol del sub beta, where beta is in n0 and then d times the Cartesian product of it. So you see, for d equals 1, this is precisely the definition of Schwartz space over R. This is Schwartz space over Rd. This is, of course, something that we need in physics, unless we always want to restrict to spatially one-dimensional systems, which, of course, we don't. So with this definition, this really goes exactly like in the one-dimensional case. We have two important facts. The first fact, which will play a role later on, is that the Schwartz space Rd lies dense, or is a dense subset. It's a dense subset of L2 of R. Aha, so we see, so we first are going to define the Fourier operator on a dense subset, and then probably we will use one of our nice theorems to extend it. But the explicit definition is on a dense subset, and the extension will be somewhat abstract. And the second fact is, of course, like in the one-dimensional case, and in fact it's the rationale behind precisely this type of definition, is that if you take Q and say the kth component, so K is from 1 to D, if you take this operator and you act on a function f, I should have said if f is in Schwartz space, if f is in S of R of D, then Qk on f is an element of SRD for any k 1 to D. Why do I write it in this funny way? Well, because, you know, it would have been more intuitive to say if you multiply f of x by the kth variable, then that function is again in here. But, you know, these are function values, so I would have to say, well, what is this function? This is the function qk on f evaluated at x. So we have this typical problem. If I want to say a function lies in a space, I can just write down the function values, although this, of course, completely yields it. Okay, so that's, of course, what we know. So you can act with the position operator, and you will not leave Schwartz space, of course, that we use several times. It's the same in RD. And similarly, if f is in SRD, then it follows that if you act with any of the momentum operators, 1 to D, on f, that result will still live in RD. Again, this is the very idea of the definition up there, that S of R is not, you don't leave it, even if you arbitrarily often, finitely arbitrarily often, apply the position or the momentum operator. So the definition of the Fourier operator now is as follows. Definition: the Fourier operator curly f is the linear map curly f from SRD to SRD. And what does it do? Well, it takes an f here and maps it to another such function in linear fashion. It's an operator. There's nothing else. It's not anything mysterious. It's an operator and has a very specific form. It's given as 1 over 2 pi to the d1/2. There are various conventions in how to choose the prefactor here of what we're going to write down, and this convention is called R convention. Okay? It has the advantage that if you do the inverse Fourier operator, it will have the same factors. You don't have to think about, oh, which one am I using? Anytime you do a Fourier transformation, its inverse, you always put this factor. Okay, it's our convention. So then you take the integral over RD, and I should say it goes to there. You see, standard problem. Everything is right, but you see it coming. So this is the function it goes to, okay? And that function is given by providing its values at a position x, and that is given as 1 over 2 pi d1/2 now the arrow points here, times the integral r to the d. Now we need a new integration variable. Let's call it y. And we go over e to the minus I xy f of y. That's it. So there's a free x on the right-hand side. Yeah, that's the one you provide here. So the value of the new function at this point of the image function is just given by this integral. It's the Fourier transform. Now, you need to delete everything you know about it. You heard of it, or not? Yes, you saw that. And there's a lot of talk about it takes you from position space to momentum space. Okay? So this kind of gives you the impression it takes you from some space to somehow a different space, or at least the underlying RD is another RD than this RD. No, it isn't. It isn't. However, in quantum mechanics, sometimes it's intuitive to think about it that way, but it simply isn't. Okay, so a word on terminology and notation. Which one first? Well, notation first. Notation. So particularly in physics, it is intuitive. It is often intuitive to think of f as a function on position space, so meaning that the argument that this f eats, f of x, that the x in RD is a position in space. While curly f of f, the Fourier transform of f, or the image of f under the Fourier operator, is a function on momentum space, or frequency space, or whatever your typical application would be. So if you take a musical signal and you Fourier transform it, you get the in a sense, histogram of the frequencies that are in the signal. So there is some sense to that, okay? And with this interpretation goes the notation, thus one often calls the variables as follows. Well, I just copy this formula. It's the Fourier transform of f. We say it actually lives on momentum space. I mean, this is classically speaking, right? So this is an RD element, right? Equals 1 over 2 pi d half integral r to the d to the dx. Now I can rename yx because what I called x here is now called y. And then you have e to the minus ipx. Oh, I should have said this ixy. What does that mean? Well, that means x1, y1 plus dot, 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 plus x dyd. And you say, well, of course I knew because that's the inner product. Well, there is no inner product, but it doesn't matter. So that's the expression. So it's d to the dx, e to the minus ipx times f of x, right? And so this is how you mostly see the Fourier transform. You start with a function on position space, as you call it, and you get a function on momentum space, but really this has nothing to do with the operator. It's just an interpretation in applications of this operator, also in quantum mechanics, where sometimes it can be meaningful to think that way. But for instance, I could equally apply the Fourier transform twice in a row. I can do that. So may I? Because, I mean, isn't the Fourier transform something that eats an object on momentum on position space? If I now act on it again, then the first action gave an object on momentum space. Am I even allowed to act on that with the Fourier transform? Or do I need to act with the inverse Fourier transform to go back? Well, of course you can act again. Why wouldn't you act again? You act once, and then you act again. Right? So this thinking, you go from position to momentum space, is too narrow. It's just an interpretation in some situations, and obviously we don't want to restrict ourselves by such a overly restrictive interpretation. Okay, so this is more like notation and a word of warning, but it needs to be mentioned. So that's notation the first. Notation the second is the age-old problem we already met with measures, and which I briefly explained with the momentum operator. Of course, we can write qk, the kth component of the momentum of the position operator, acting on f. We know what that is. That is the object that if you evaluate it at x, it's given by x to the k times f of x. But, well, what is here in brackets, that's an element of S of Rd, and what is including the x, and therefore also the right-hand side, that's just an element of the real numbers, right? Because, yeah, full stop. Now, the Fourier operator acts on this SRD set, so it's meaningless. Formally, it's meaningless. Everybody would understand what you mean, but we want to be a bit more precise. It's formally meaningless to say the Fourier transform of fxk of xk times f of x. What is that? Anybody can solve this exam problem, but it's meaningless because this is an element of R, and the Fourier transformation can certainly not act on it, but it can act on qk of f. Clear? It's a very simple thing. Now, it would be very, very tiring if all the time, if we have to do something by multiplication, it's a bit more complicated, like e to the tralala, if we always had to define the action of an operator in this fashion and then to say it's the Fourier transformation of the such defined operator. It's just a lot of writing, okay? So therefore, to lighten the notation, it is sometimes useful to let an expression of the form f of x, and then you put a hat over the whole thing, including the x, to let this mean a function of p. Well, I don't need to write this first. I mean, by this, I mean the f, the Fourier operator applied to the function f that is defined by the function values f of x. this is, of course, terrible formally, because on the left there's an x appearing and on the right there isn't. Okay? So it would be more meaningful. So this is what we say. This is just a short notation that I just explained. It would be a little more meaningful, well, it would become really meaningful, if we wrote this as the hat over the assignment that an x is assigned an f of x. That now makes sense, because x is assigned f of x is an expression that doesn't depend on x. It's a prescription for a map. And the Fourier transform of that map is written like this. So maybe one could write this thing here up here better. Another alternative would be to write f of x is being sent to xk times f of x. That would make sense again, because then you have a map in here, but this is also a lot of writing, right? So we opt for, so all of this, this doesn't make sense where the question mark is. This is a very strange form of writing it, but if you read it right, you know what we mean, okay? So strictly speaking, you can't ask for the Fourier transformation of 1 over x squared or something. Well, anyway, you can't. But you cannot ask for that. You can only ask for the function that has this function prescription. Okay, so this is the hat notation. And very often in books, it even becomes the f hat notation. And then, of course, you write f hat of p, because the whole result depends on p. This depends on p. Just another variable. Okay? Okay. Good. So much about notation and its confusions. I tried to avoid this, but in some instances it would really be very cumbersome to write it differently. So we have a little proposition, which in fact is the key of what you use very often if you do very quick calculations in physics, in quantum mechanics. So let f be a Schwartz function, and let gamma be some multi-index, so n0 to the dth Cartesian power. Then you have A, that if you first take the derivative del gamma of f, what does that mean? Well, you take the derivative in the first direction, gamma 1 times, you take it in the second direction, gamma 2 times, and so on. You first take the derivative, and then you take the Fourier transform of it. What will you get? Well, at the point P, you will get the same as if you had taken, yes, I can write now the I on the right-hand side, but I think it's more memorable for you if I put the I on the left-hand side. So you take minus I times this arbitrary derivative. But then I have to take it minus I times to the order of this gamma, which I'll explain in a second. So what will I explain now? What does this order mean? Very simple. The gamma is a tuple in n0d, and the order of gamma is gamma 1 plus ... plus gamma d. So you take all the components and you add them up. And obviously, if you take the derivative in the first direction, gamma 1 times, and then this derivative in the second direction, gamma 2 times up to gamma d times, then in total, you took a gamma 1 plus plus gamma d derivative. Makes a lot of sense that this minus I that usually comes with a single derivative, if you think of the momentum operator, comes with the same order. So you do that, and then you apply the Fourier transform, and the result is that is the same as if you had first applied the Fourier transform to the f without doing this thing at p and multiplied the result by the p to the gamma, meaning p1 to the gamma first power, p2 to the gamma second power, and so on. What does that mean? It means, forget about the Fourier transform on the left-hand side. You can take here the momentum or a product of momenta and their powers on a function. And that's a complicated thing because you have to derive and stuff like this. But instead of doing that, forget everything that's written there, you could just take the Fourier transform of the function and multiply it by p gamma. That's multiplication. And that result are related by a Fourier transform. So physicists say if this momentum operator product applying on position space, the physicist says, you can map the result to momentum space where that action, if you had first mapped to momentum space, would have been represented by multiplication. Aha. Interesting, because it seems like the momentum operator, if I intertwine with this Fourier operator, it seems to become a multiplication operator like before we had on position space. The position operator acted as a multiplication operator. But apparently with this Fourier transform, I can do a transformation, which is a unitary transformation as it will turn out, right, and represent the same operator in a different form. In fact, you can represent every self-adjoint operator by a suitable transformation. The Fourier transformation is adapted to this momentum operator, such as to represent any self-adjoint operator by simple multiplication under a suitable unitary transformation. Anyway, so that is what one says. The momentum operator, here even products of them, are represented on momentum space by multiplication. You say, aha, and what about the position operator? Is that then still also represented by multiplication? Well, certainly not. So you can ask the question, what happens if you first take x to the gamma, that means x1 position to the gamma first power and so on F, and then you take the Fourier transform. You can ask the question, so at the point P, you can ask the question, how does this relate to the expression where I first took the Fourier transform? I keep saying transform, but it's right. So the Fourier transform, and how do I have to act on the Fourier transform if I now want to understand the position operator? It turns out it's I, not minus I, but it's I times the derivative of this thing in the gamma direction. So it would really just exchange P and Q if I had a minus here. But it doesn't exchange P and Q. It makes the P to a multiplication operator, say a Q on there, and it makes the position operator to what looks like a momentum operator up to a sign. Yes?
But shouldn't we have I to the power?
Yes, of course. Yes, thank you. Exactly like this. Have you seen some behavior like this before where X's, or thinking physicists, where you have a pair QP and it's being mapped to a pair P minus Q? Minus PQ. What is that? In classical mechanics, that's a canonical transformation. That's a canonical transformation on phase space. So this kind of simulates that. Anyway, this is just not relevant for the exam, so you can cross it out. Okay, good. So we have this these two facts. Well, let's very quickly prove that. Okay, well, let's start on the left-hand side. F of minus I to the gamma, del gamma F. Do we want to do that in that? Well, it suffices, look, it suffices to do this for So it suffices to do this for order of gamma is 1, and then I have to take one of the directions to the ones. So there's a 1 here, and I choose the kth direction. Obviously, if I can do that, I can do that. I just have to repeat. Okay. So we look at this guy. Well, what is it? We evaluate at p, say. That's then 1 over 2 pi to the d half. Integral r to the d. dx, dd to the d to the dx. E to the minus ipx. And then we have a minus I dk on f at x. What can we do? So where do the functions f come from? The functions f come from Schwartz space. So let's do an integration by parts. How does that work? Well, you get an overall minus sign. Now the derivative revolves over here. It acts on here. This is a function of x. So it acts in the, derives the kth component of x. So it's a minus ipk as a factor from here. You have another minus I from here. The e to the minus ipx is of course recovered. And there is the f of x plus you have a surface term. You have to look at e to the minus ipx with all the garnish of the numerical factors times f, but you look at this on the boundary of Rd. Well, the boundary of Rd is far away, and these are very rapidly decaying functions, faster than any inverse polynomial, and so you can drop the surface term. And then you have this thing. You have a minus I, another minus I is a minus 1. You have another minus is a plus. Equals 1 over 2 pi d to the 1/2 integral. And the pk can jump in front because the integral is over x. Pk e to the minus ipx f of x. But if I then collect the factor in front of the integral, this is pk Fourier transform of f at p, which thankfully would be the claim if we had extended this to repeated application of this, which you can show by induction. Okay, so this is the essential calculation. The rest is induction. F of, you see here I already did what I wasn't supposed to do. I wrote x to the gamma f. What do I mean by that? This was meaningful because this is still a function, but this is not defined. This is not a function. This is something very terrible. So I have to correct this. X is assigned x gamma f, and with my previous notation, I could call this x gamma f of x hat on top. Okay, sorry. Everybody means what you know. Let's be a little precise, and then we can be sloppy, but not in the other order. Okay, so have f. Now this makes sense again here. Where am I? Exactly there. So f of x is assigned x gamma f of x. Also meaningful. What is that? That is 1 over 2 pi d 1/2 r convention rd d to the dx. The result is supposed to be at p equals e to the minus ipx. Now I can write x gamma. And here we do the same logic. We do it with the kth component, and that suffices. X to the k f of x. Now this is a similar trick. Equals 1 over 2 pi d 1/2 rd. Now it's very tempting to write something like d to the dx and say, if I derive this guy here with a factor of I with respect to the kth component of p, So the standard notation would be something like this, derived with respect to the kth component of P, the object I minus IPX. Of course, what I get is the e to the minus IPX times minus I times I is 1 times the kth component of the P, of the X, which is exactly what is written there. So it's tempting to write this, and of course, again, everybody understands. It again looks a little like this is another space with other variables. Actually, what is much more meaningful, the partial derivative acts on the kth component of a function, right? So I cannot let a derivative act on something where there's an x in it. A derivative, it can act on a function, but not on function values. You agree? It's f prime of x, not f of x prime. But here we seem to do that. Everybody knows what you mean, and please do it if you can't avoid it. But actually much clearer is if you say you do the derivative in the kth direction of the map here that's understood as P is being sent to I to the E minus IPX, because now even I understand what you mean. There's a map that makes this thing. X is a constant for this map, obviously, and you do the derivative with respect to the kth direction. That is what this means, but this is kind of high school, well, bad high school notation, right? Bad to be associated with high school, not with notation. And this is meaningful, okay? Okay, but in any case, this is this rewriting here. Okay, what did we want to do? We wanted to get, now I confused myself. Excellent. Derivative with respect to P. Yes, it's a derivative with respect to P, so I can pull it in front of the integral, because the integral has nothing to do with the P, right? It's just a constant in there. Well, of course, you can argue with dominated convergence, blah, blah, blah. So then you get integral RD, d to the dx. The I jumps out too. Why would it not? E to the minus IPX f of x. And this is I del k of the Fourier transform of f. Only after the derivative is being performed, you evaluate at p. Of course, it's a derivative. And again, by induction, the general result follows. That's true for AS2 as well. So by induction, the claims A and B follow. So there are a number of properties for the Fourier transform. You maybe saw that in the mathematics courses, like there is convolution, and there is what happens if you shift a function, then you pick up a phase factor. What if you take a function, you evaluate it at a multiple of its original argument? Well, then you have the Fourier transform of that is you evaluate the function at the inverse multiple of the p you get times a factor. So let's note two of the ones we need quite often. So it's yet another proposition. I know this is all terribly boring, but useful. Proposition. So f in the Schwartz space, of course. So you have A is you take, you see I use this funny notation again, you take f not at x, but you shift it by an amount A. So you shift the function, and then you take the Fourier transform of the function defined by this prescription, by these function values at p. And what is that? That's the Fourier transform of the unshifted function, so f of x, that function unshifted, but you get a factor e to the IAP. Well, yeah, because this depends on p, and this is the multiplication here, e to the IAP. So a shift translates into a phase. We saw that before, right? Find out where. And B, also interesting, you take the Fourier, you take a function, but you blow up, well, rather you shrink the function on the x-axis by giving a factor lambda, and then you take the Fourier transform of that function at P. What does that give? Well, that's something very typical. Look carefully. It's the Fourier transform, not of f of x, but of f of x divided by lambda. Yes. The Fourier transform. No, hang on, that's not true. It's the f of x Fourier transformed and the p is divided by lambda. Isn't that right? Yes, I must be right. Everything else makes no sense here. That's right. Okay. So you take the Fourier transform of the f, but now the p is divided by lambda. That means if you shrink, so again, if lambda is 20, you have a function f of x that looks like this. If you then evaluate it and you pretend you're already at 20 times the position where you really are, then the function gets shrunk. So for lambda greater 1, this shrinks the function along the x-axis. But then the Fourier transform of it will be spread by the same factor, the inverse factor, however you want to express that, along the p-axis. Okay? So shrinking in position space makes expansion in momentum space, the physicist says, or rather this, but there's also a correction factor, and it's 1 over lambda to the dimension. But that's just a numerical factor, so it gets spread, and at the same time, if lambda is greater than 1, it gets shrunk like this to preserve the area under the function, well, the squared area, so the integral over the square is preserved. It's called Parseval's identity, and that will be instrumental later today. Okay, so again, proof from the definition immediately. So you can do this as a homework exercise. That's good practice to work with the definition. And they're meaningful. Now this has to do, well, very roughly speaking, this has, well, not very, it really has to do, it's at the heart of the uncertainty relation. It's just the uncertainty relation is much more generally valid for any operators. You don't have to be on L2 of some RD and so on, but on L2 of RD, this is in one way the expression of the uncertainty between position and momentum. But again, it's the uncertainty relation is something much more general. But that's actually originally how Heisenberg is rumored. I say it's rumored. I mean, people certainly know whether this is, in what sense this is true, but I'm not a historian of science. So modulo idealized history. This is what Heisenberg said. Well, look, I mean, you have these relations here. There is something with uncertainty, and then he came up with his matrices and so on and so on. I don't know whether it's the right order, but it's a good fiction, and so I tell it. So let's look at the inverse of the Fourier transformation. Is this 3? No, 2. Inverse Fourier operator. Or I should say the inverse of the Fourier operator, because we already have it. Well, it either is invertible and has an inverse, or it doesn't. So there's nothing to be defined, but there's a theorem that says the Fourier transform, as it is defined explicitly on Schwartz space, is invertible and its inverse, well, no secret how that is denoted, f inverse of f is the following expression, where we again define it not define it, we express it pointwise. It's already defined. It's just theorem. At x, or according to the physicist convention, you go from x to p by the Fourier transformation. You go back to the x space if you come back. But again, this is empty. It's just maybe a mnemonic at best. This is 1 over 2 pi d1/2, beauty of our convention, it's the same prefactor. Integral rd, d to the dp now, well, because we're going back to x, we integrate over p, e to the plus I px. Okay, so it's the inverse one that has the plus, whereas the Fourier transform has the minus. Remember, okay, remember. Times, well, you see this f was now the Fourier transformed one, so we call it f of p. So maybe, just for pedagogical reasons, let's call this the g, because it could have been, the g could be the f of an f, okay? But of course, again, this is empty, this is just notation. Good, so that's the theorem, and that is interesting enough, and the techniques we now need are interesting enough to prove it. So there are all these physicist formulae around, which are of course right. It's like something like e to the I p x minus y is something like the delta function, right? I don't know whether you saw something like this, the integral over p over it. But this is very convenient to use if you always use it in the same context and you learn the trade of the game. But it's somewhat mysterious, so, well, it's better to have a proper calculus that you know how it works. And in fact, in order to prove this theorem, we need a lemma. And the lemma is the following. Lemma. If you look at the function exponential, it's a very special function, exponential of minus z12, but z is now just a complex number. But in fact, for technical reasons, we have to restrict to the real part of z being positive. So it's the right half plane of the complex, right half plane of the complex plane without this axis. So that's where your z may lie. X minus z half times x squared. Well, this x squared, well, I don't know, do we do this in one dimension or what? Yeah, let's do it in one dimension. It suffices, I mean, this is true in d dimensions, but because of the structure of everything here, it suffices to do it in one and then you recompose it for several. So let's do it in d equals 1. And so the x simply comes from r. Okay? But the x is supposed to become an Rd element, and in the general case, the z still remains just a complex number with positive real part. You look at this thing, so it's a Gaussian, right? You know how that looks like. This is something like this. And if you make the z bigger, you shrink it, right? So big Z is something like this. So big Z. And smaller z is like this. No? So that's the Gaussian. And you take the Fourier transform of the Gaussian, and what you get is a Gaussian, but the z jumped to the denominator. There's still an x squared. And here you get 1 over the square root of z. Now you probably did calculations like this before, like you, well, no, maybe you didn't. Okay, so anyway, that's this thing. And if this is in d dimensions, you get up to the power d here. So let's maybe write down the lemma in d dimensions so that you at least know how to generalize this. Okay, then it looks like this. And obviously the x squared in d dimensions is what you would suspect from undergraduate physics. We mean, of course, this expression here. So, So proof of that. Well, let's first define a function that I call the Gaussian controlled by z. And that's exactly the left-hand side without the hat. At x is supposed to be x of minus z half x squared. So the proof is now solidly in d equals 1. Okay, this is this function, this Gaussian thing. Now you can derive it. Why not? With respect to x. So you take the derivative del, well, there's only one direction, so I just write L, del gz, and then we evaluate at x. What is that? Well, the right-hand side with respect to x is minus a z, the 2 and the 2 cancel. An x comes in front, inner derivative, times the outer derivative x of minus z half x squared. Happy with that? I think so. Equals minus z times x times the Gaussian controlled by z of x. Also true, huh? Looking at the equation in the box, we see it's a differential equation for this Gaussian. So this is an ODE for the Gaussian, and we can actually, pardon me? It's an ODE for the Gaussian. No, hang on. No, what am I doing? No, hang on. No, we have to think a little more. Okay, sorry. We're not looking at the box yet. I tried to be too clever here. So, what did I want to do? Yes, of course. Okay. So I want to rewrite this derivative action on this space. I want to derive it as a multiplicative action on the Fourier transformed bit. But that's only true if I have a minus I here, right? Because minus I del on the x space is the p on here. But because I don't have the minus I here, I need to put an I there, and it becomes true. Do you see that this is something we had in the proposition before? And here I have x times gx. You say, well, that's perfectly fine, but I can rewrite this part as I times, not minus I times, but I times the derivative of the Fourier transform of the gz, all evaluated at p. And then on the right-hand side here, so if I take the minus z as well, I have this right-hand side and I have this left-hand side. So this is by the two prepositions, the second last one, where I explained how you can represent the momentum and the position operator on the non-Fourier transformed function as multiplication, respectively, differential operators on the Fourier transformed part. Okay? So now this is what I wanted. Now I have a left-hand side, a box, equals, well, it's not really a box, equals this thing. So what is this? This is a differential equation. So this is an ODE, an ordinary differential equation for the Fourier transform of gz. So here we calculate the Fourier transform by first writing down an ODE for that Fourier transform, which follows directly from the definition of this function, an ODE that we can solve. I'm puzzled. No, I'm not. So, okay, so there's a derivative, there's the function itself, so we we solve by separation, which can be solved by separation. So we have here the del f of Gz. We can divide that by the f of Gz. And this equals, now I have to think about the signs. I go there and I divide this through, is an I, it's a P, it's by Z, it's a minus sign, and it's divided by another I. So it's minus P over Z. dP. Well, because this here is a derivative with respect to P, so if I do this which calculus here, where I separate like this, okay, this is where your method course comes in handy. So you see you have this here, and of course now you can do an indefinite integration on both sides. And of course what you get is you get on the left-hand side the logarithm of f of Gz equals, on the right-hand side you get minus 1/2 p squared over z plus a constant of integration, and because we're complex here, so it could be complex. So now you can exponentiate both sides, which yields f of Gz equals plus or minus, because I also get rid of the absolute value. But anyway, I have an e to the c. The c can be complex. Well, this all absorbs into a complex a times exp of minus p squared over 2z. Doesn't look too bad, because that was my claim. I claimed the Fourier transform of this guy is some factor times x minus 1 over 2z x squared. Well, that part I got. What remains is to determine the a. And of course, this is at the point P, and I should also say here at the point P. Okay? So how do we get the A? Well, now, if I look at the Fourier transform, you can evaluate the whole thing at the point P equals 0. And the definition of the left-hand side here is, of course, 1 over 2 pi to the d half. Okay, we're in one dimension, careful. We're in one dimension, it's just 1/2. Integral r to the d dx e to the minus ipx of this guy is e to the minus z half x squared. That's it. And the right-hand side is simply a times e to the tralala 0 is 1. So you have an expression for a, but on the left-hand side you also replace the p by 0. So then that factor is simply a 1, and you are left with the integral over, well, rd is wrong, it's of course only r, integral over r e to the minus z half x squared. Well, you find that this thing, well, this you certainly did. You certainly calculated once in your life for real z what this is. And it is square root of pi divided by z. 2z? No, z, right? I think it's z. It's z. Right. Is it? No, I don't think it is. It is, you have to, whatever is in front of this guy without the minus, you have to divide through. So it's 2 pi over z. So that's my rule. So my rule is, well, my rule, it's the truth. E to the minus sigma x squared dx is the square root of pi, not times sigma, but divided by sigma. That's it. I think that's right. So if there's an extra 2 in there, got to take care of it. This equals, yeah, exactly, because otherwise this doesn't cancel. So what this yields is 1 over square root of z. Done. So A is 1 over square root of z, which is precisely what the claim was in one dimension. There you go. So that was just the lemma. So the lemma was, no, we're not done. We're not done. So this is true for z in the real numbers. But we will need it for complex z as well. Now, this is not so simple, because if you have a complex number and you take the square root, you have several possible branches. So you have to, in order to say what you really mean by the square root, you have to place a so-called branch cut. And in this case, we place it along the negative real axis. Did you do some function theory? Do you know branch cuts? Who knows that? Okay, and the rest doesn't? Okay, ignore. Okay, ignore. Can do that too. And the logic now here is that you can extend it, since the integral above is holomorphic in z. So this is a notion from functional analysis. It essentially means it's complex differentiable in z, but in the complex numbers, differentiability is a stronger notion than on the real numbers. Why could that be? Well, because differentiation has to do with limits. You take the limit of a differential quotient. On the real line, there are only 2 ways you can approach a point, a left limit and a right limit. And you know that the derivative only exists if the left limit of the differential quotient and the right limit coincide, so if the limit exists. But in the complex line, you can approach this in many more ways than in the real line, and that gives a stronger condition. So differentiability on the complex plane of functions on the complex plane is a much stronger criterion than on the real line. And in particular, every complex differentiable function is Taylor differentiable, is Taylor expandable. So all differentiable functions are actually analytic. Okay, there is a Taylor expansion. It's very strong, because in the real line it's absolutely not true. And holomorphicity is just the learned term for exactly that fact. It's differentiable, it's Taylor expandable, blah, blah, blah. Okay, the integral is, since the integral is holomorphic, we can extend the result to complex z with real part greater than 0. Okay, this is really a technicality. Don't worry if you don't have the background. Proof. So it's a proof of the actual theorem. It's the proof that F inverse as given is F inverse. So how do you verify that something is the inverse? Well, you apply it and you see whether it's the identity if you apply it to the result of the first one. So F inverse of F on F, so say F is of X, then F of F is of P, then F inverse of F is of X. Let's do that like this. So you're back here, equals. Now let's first work on the outer inverse Fourier transformation. I just verify that as given it is that. So I use what is given in the theorem. The theorem claims this 1 over 2 pi d half integral rd some dp e to the plus ipx. Why plus? Well, it's the inverse plus ipx. And there we got an f of p and the dp I already wrote down d to the dp. Okay, not much happened. I just wrote what was given in the theorem. Now, if you continue from here and you just keep on calculating, you get into trouble. So what you need to, it's fine, what's written there is true, but you need to massage this expression a little. One calls this a regularization maybe. You insert a 1 here. You insert a 1. And this 1 has the rather idiosyncratic form that you say you insert the 1 in the form exp of minus epsilon half p squared. I think that's the form I used. That's the clever one here. And, well, that's not a 1, but if you send the epsilon to 0, it is a 1. I mean, what's the idea of doing something like that? Well, it's supposed to help us with the convergence behavior, to see the convergence behavior. Nothing happened, okay? This one is this thing. The limit is to be executed first, and then you get a 1, and that's what it is. But now, think about it. How does this guy look like? And now it's important to really get the discussion right. At p equals 0, this is e to the 0 is a 1. And if p is bigger than 0, whatever epsilon is, the epsilon will only stretch or squeeze it. The function will always lie below 1. Agree? It's a bell curve. It lies, bad bell curve. It lies below 1. If this thing converges, if this exists, which it should be because this guy lies in S of Rd, and we know we can do this transformation. The plus or the minus just gives a minus or plus here. We know that integral exists. The question is it the inverse? You know this exists, so you know if I take the product without the limit of this guy with that guy, the result will be a function that's dominated by the previous function. So if the previous function, whatever it is, and you multiply by this, all you do here, you keep that value, and here you pull the previous function a little down, right? So certainly the product of the f with the x is dominated by this guy. Dominated. Lebesgue integral. Dominated convergence tells you can pull out the limit. Beauty of the Lebesgue integral and beauty of the construction of the factor, of this regularization factor I introduced. So I do the limit in the end, but meanwhile, before I take the limit, I always consider d to the dp exp minus epsilon half p squared e to the ipx f of p. So before I take the limit, I now have this expression. Maybe I do this in blue again. And this is a very general trick. It seems here like something very exotic, but it's a very general trick. It's what we call regularization. You have an expression which, if you really want to calculate it, seems somehow technically not convergent. There is some issue there. And you make the expression more manageable by introducing a so-called regularization parameter. That must be done in such a way that if you take the regulator, if you have the limit immediately in front of the regulator, you remove the regulator. But it, of course, only makes sense if you can show that you introduce a 1 like we did, and then you have a theorem that tells you that you can first regulate, then calculate, and then take the limit again, that's the same as first taking the limit and then calculate. Of course, otherwise it's not an equal sign. Okay, so sometimes this regularization procedure is surrounded by some mystery because you say, you regulate and then in the end you take the limit. Well, why are you allowed to do that? In this case, it's dominated convergence, the dominated convergence argument or theorem, dominated convergence, which we discussed earlier, of the Lebesgue integral. So you saw your first regularization in quantum field theory. If you calculate stuff, you do this all the time. Okay? Okay, good. So you have this guy. And now we, as I said, the plan is to keep this limit till the end and only execute it in the end. Equals, okay, limit. Well, I'm not writing. I look at this integral. This is, of course, r to the d, d to the dp, exp of minus epsilon half p squared e to the ipx. Now I also execute this Fourier transform. And, well, strictly speaking, the integral is over here. Well, let's do it like this. This is rd. Now, this b, I call this d. Well, dx is now dangerous. I should call it dy, because dx is already being used. I need another integration variable, e to the minus I p x, because the Fourier transform. So that's a minus f of y, I p y, f of y. Okay? So in the next step, I would like to pull this integral over y, dd y. I want to pull it in front of the integral ddp. Which theorem, if any, allows me that? Fubini. Fubini allows you that. So this is the integral rd ddy ddp exp minus epsilon half p squared. And now, what do I want? Yes, I want to take this guy into here plus ipx. I can do that. Now it's 2e functions. Okay, it's 2e functions. And then I have e to the minus ipy fy. Yes. So I can now take this bracket here. No. This bracket there. So all the p's are covered by that. The y is still outside, and this y is outside. Well, so here y is the free variable in the square bracket. And what this is, of course, is this is exp minus epsilon half p squared plus ipx Fourier transformed, result evaluated at y. Why? Because this is a function of p, parameter x, nobody cares. Yeah, x is free, yeah. Parameter x, function of p. I can Fourier transform it with e to the minus ipy, and that is now the Fourier transform acting on a function of p. Do you remember my comment in the beginning? This is exactly the case where we apply the Fourier transform to a function of p. You would think, no, Fourier transform is applied to a function of x, and the inverse is applied. Well, no, it's just free, right? It's just a Fourier transform. Okay, so this would be something where the intuitive physicist, with all his intuition, would get stuck. So, okay, so we just continue. Aha. So now we have to understand what the Fourier transform of this thing is. Now imagine the e to the plus ipx term wasn't there. Well, we just calculated what that is in our little lemma, what this thing is. So let's write down what it was if this extra term plus ipx was not there. So we would have a ddy and then a 1 over the square root of the z. But the z is now an epsilon. And so we have by square root of epsilon, previous lemma, times, we know it's a Gaussian again, but it's a Gaussian where you now divide by epsilon. So minus 1 over 2 epsilon jumped down, like in the lemma. And of course, it's of y squared. So this would be the result if there was not this additional bit. Now you can play a game I'm tired to do, because I did 3 times this morning, got 3 different results, but I'm confident the third one is the right one. You add, what do you call it, binomial completion, you know what I mean, right? So you add a term that makes this into a square of a sum, or rather of a difference, and then you subtract it again and bloop, 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 bloop. And what you get in effect, if you do that first, then you get the result, this is y minus x squared. So this extra bit has the task of shifting the y by this free x parameter. Okay? And then you have an f of y. I hope I didn't forget anything. Yes, I of course forgot something. I forgot to carry the limit with me. So the limit, of course, goes everywhere there. So now we want to massage this away, this crazy bit. So we do a substitution in integral to make the exponent simpler. So we do a substitution that says z equals okay, I'm sorry. So if we're really in d dimensions and I use the lemma, I have to write the square root of z, which is here epsilon, to the dth power, you remember? So now we substitute z equals square root epsilon, no power, of y minus x. If we do that, then of course the measure d dz becomes square root of epsilon to the dth power dy, ddy. Should be right. So what the integral becomes, I repeat the left-hand side, f inverse of the f of the p of x equals integral rd. Did I drop? Ah, yeah, and I dropped, I also, I should have taken this power, of course, also with me, as you can easily see. So this is limit epsilon 0, 1 over 2 pi to the d half integral. Now we performed the substitution that leads to a, yeah, excellent, to a square root of epsilon to the dth power from the measure. Not good. Well, of course I didn't want that. Why don't you complain? I of course want 1 over square root epsilon. So it's 1 over epsilon to the d half. Of course I want that, because you'll see now in a second. So this is therefore 1 over epsilon. No, it's epsilon to the d half. Now, because I have to replace the dy by a dz, so this one needs to move over here. So it's a factor here. So we get this one from the measure, but now consistently, of course, we have x minus, we have a factor 1 over epsilon d half, because it was there before. And now it's the exp of, well, if now the z is this expression over there divided by the epsilon, because there's a square and in front there isn't, this is minus 1/2 z squared. Am I right? Times f, and now I have to replace the y, but the y is the z plus the square root of epsilon, z plus the square root of epsilon x. If I solve for y, no, yes, no, oh, come on, x of square root of epsilon z is my next proposal. You see, this is how it went the whole morning. So you solve for y, that means you first multiply by the square root, it's the z, and then you add, yeah, that's it. Okay, that's this. And now? Well, this is a z integral. Certainly, I can now pull the limit in again. And I get 1 over 2 pi d half. No, I'm worried. Where has my...
It's 1 over 2 pi to the power of d.
Here?
Yeah, we're missing from the Fourier transformation, we missed the 1 over the power.
Yeah, but... Right. So we have the second Fourier transform. That second Fourier transform introduced an extra factor.
Yeah, but did we pull that back in when we wrote the exponential functions Fourier transform?
I can't listen. Okay, again.
So we should have pulled the d half back in when we wrote the exponential function as a Fourier transform. Down.
Yeah.
When you put the half on the thing.
Yes, okay, so so we replaced Fourier, we put a Fourier transformation here that I forgot the factor. That's first of all for sure. Okay, so let's put that there. 1 over 2 pi d half. So that's there. It gives a total factor d.
Yeah.
And then
it also carries to the next line.
yes.
But then you pull it back into a Fourier transformation, so the factor gets pulled back right underneath. So the factor gets pulled in again.
Yes. If I do this one.
Yeah.
So it's that. It's that. Yeah. Okay.
And the 2 pi will vanish integral over your Gaussian.
Right, because it doesn't see the limit. Yeah. Excellent. Thank you. Okay, I was unnecessarily concerned. Thank you very much. Okay, you reassured me to no end. Okay, so let's continue here. So the point is, you have this thing here. Now you have this integral d to the d z e to the minus 1/2 z squared, which can simply be calculated. But you pull the limit past, so this is epsilon goes to 0. Epsilon d half by epsilon d half is gone, and all that's left is f of x plus this guy. Now I can calculate this first, which is of course nothing but f of x. F of x will jump out of the integral. The prefactor, however, thank you for the remark, that's of course exactly here the square root of pi divided by the prefactor. That is of course then pi times 2, and then it's the dth power because we have this integral d times, and that of course cancels precisely this, so we have f of x. So that means f inverse of f is f. And that's the claim. Okay, so it's this fiddling around with these objects. Good. I mean, there's technically nothing. I mean, the interesting bit is this regularization idea, removing a knot, and the rest is, well, calculating right, which is a challenge in itself, but it's not a mathematical one. So we come to the final statement for today. And that's the very important way to look at the Fourier transformation. It's the extension of the Fourier operator to the whole Hilbert space, L2 of Rd. Now we already know that f is densely defined simply because S, the Schwarz space over Rd, is dense in L2 Rd, so it's densely defined. The domain of f is dense. Under what circumstances can we extend a densely defined function to the whole Hilbert space? Yes? If it is bounded. If it is bounded. So is f bounded? What do we need to calculate? We need to calculate the operator norm to check whether f is bounded. Calculate the operator norm of f. It's nice to understand that this is an operator. Well, trivial. So the operator norm of f. What is the operator norm of f? It's the supremum over all f in the Schwarz space, well, in the domain, of course, over the quotient of f applied to f, yeah, divided by f. What is that? Well, that's the integral over d dp, absolute value of f of p squared, divided by the integral d to the dx of absolute value f of x squared. Right? Because you need to use, of course, the norm on S of R that has been inherited from the ambient Hilbert space L2 Rd. What do we know about this quotient? Well, there's a theorem, and it's called Parseval's theorem. Parseval's theorem says that you can take this integral, the square integral of the Fourier transform of a function, but that will be the square integral over the function. That's Parseval's theorem. Proof by direct calculation. So Fourier transforming a function does not change the norm. Hence, the operator norm of f is 1. I think what I wrote up here is not entirely right, because this would be the square of the norm, right? What I wrote here is the square of the norm. It's not the norm. It's the square of the norm. So I have to take square roots. But nevertheless, the result holds true. The operator norm is 1. So it's bounded. Aha. So we have a densely defined bounded operator, dense with the main dense on L2 of Rd, is important dense in what? In that Hilbert space. So it follows again by the BLT theorem. Implies there exists a unique extension of F to, well, F of course still, but now on all of R L2 of Rd. Now you say, why didn't I write this down immediately in the beginning? Well, the point is, the explicit definition with the integral e to the minus IPx can only be executed on Schwartz space. This is an abstract result. It says that it exists and it's unique, the extension. But if you look at the proof of the BLT theorem that gave, there is an explicit construction in there, how that works. So in practice, what you have to do, if you want to do the Fourier transformation, so in practice, or whatever practice means in theory, in practice, if you want to do the Fourier transformation of an f that is in L2, but not in the Schwartz space, what do? Well, you have to approximate that guy. You have to approximate it by, as a limit, in some way, over some n to infinity, of some functions fn, where every single f lies in the Schwartz space, and the limit equals the f that you look at. You have to approximate the f by a sequence in Schwartz space. Why is there such a sequence that approximates it? Well, that's precisely the statement that it's dense, that Schwartz space lies dense in there. But now it's a bounded function, but a bounded function, not function, bounded operator is always continuous. So the limit can jump out. And this is always defined because every single fn is in Schwartz space. So you need to approximate it, and then you do the Fourier transforms of this family, of this sequence, and then you take the limit in the end, and that's the definition of this extension. I mean, this is how it always works. Okay? You see, I mean, all these things we did, that bounded operators are then continuous. So you need this in order to make sense out of expressions, right? So the sometimes a little sloppily defined Fourier transform, you have it actually technically defined only in Schwartz space, but BLT guarantees you unique extension to all of the Hilbert space, and that's the practical prescription how to calculate the Fourier transform of an only L2 but not Schwartz function.